Hello and welcome to another session in physics. In this session we'll be looking at the topic sound waves and sound waves production. We'll also be looking at transmission of sound waves, things like speed, echo and its application, reverberation, characteristics of sound, forced vibration and resonance. But before that, let's take a review of the previous lesson. Welcome back. At this point, let's see what we mean when we talk about sound waves. Sounds are just waves, just like every other waves. Already in our previous lessons, we've been focusing on light waves, but today we're talking about sound waves. And sound waves are simply a product of vibrating objects. Some of the sources of sounds could come from when people talk, when people shout, when there is beating of an object or beating of drums. We could have blowing of flutes, shooting of a rifle, the ringing of a telephone, noise from moving cars, aeroplanes and musical instruments. Either way, take note of the fact that sound waves are produced by the vibration of objects. Now, how is sound transmitted? At this point, let's talk about transmission of sound waves. Remember that just like every other wave, sound also is capable of traveling from place to place. One of the characteristics of waves is that they have the capacity to move either through a medium or without a medium, but either way they have the capacity to travel through space. And sound waves are not an exception. So sound travels from place to place as sound waves. Now, sound must have a substance for it to travel through. In other words, sound does not travel through a vacuum. Sound needs to travel through a medium, and there is nothing in a vacuum that would pass on a vibration. Therefore, for this reason, we say sound waves are longitudinal waves. What it simply means is that the air vibrates backwards and forwards in the movement of that waves. In other words, the movement of the waves causes it to vibrate either forwards or backwards. So, sound waves needs a material medium for its propagation. Sound can travel through solids, it can travel through liquids and through gases. It is the air change, the air that changes into vibration, that is carrying these impulses into the brain for interpretation. Let's look at characteristics of sound. Sound has so many characteristics. One of them is what we call pitch. What is pitch? Pitch is a characteristic of sound that depends on the frequency of the sound waves. So what it simply means is that if the frequency is increased, the pitch of the sound also increases. If the frequency is increased, the pitch of the sound also increases. The reverse is also the case in such a way that if the frequency is decreased or reduced, the pitch of the sound also decreases. What about loudness? Well, the loudness of sound depends on what we call intensity of sound. The intensity of sound simply refers to the wave, the rate of the flow of energy of that sound per unit area perpendicular to the direction of the wave. I'll take that again. The intensity of the sound of wave is the rate of flow of energy of that wave per unit area perpendicular to the direction of the wave. Intensity is proportional to the square of the amplitude. So what it means is that the greater the intensity, the louder the sound. So when you hear about loudness, the first thing that should come to your mind is the intensity of the waves, the intensity of the vibration, the intensity, how strong the energy is. That is what leads to loudness. What about quality of a sound? Quality of a sound simply refers to a property which enables us to distinguish the same note that is being played on different musical instruments. For example, if a particular musical note is being played on a piano or on an organ, a mouth organ for instance, you would note that due to the differences in the instruments, the quality of the musical notes will depend on the harmonies. So even though they may not necessarily make the same sound, but their quality would definitely be the same. It is this property, this quality, that helps us to distinguish that this note is the same, but it is being played on different instruments. Now, when a note is produced, the strongest audible frequency heard is the fundamental frequency. All other frequencies that are present are called harmonics or overtones. What do we mean by forced vibration? If a tuning fork A is struck and then stopped, you will discover that it will cause the tuning fork B to vibrate, provided both forks have the same frequency. This is what we call forced vibration. Other forms of forced vibrations include 1. Resonance. Resonance is a very special case of forced vibration because it occurs in a system when that system is made to vibrate at its own natural frequency as a result of forced vibrations it has received from other sources of the same frequency. Resonance occurs in a system that is made to vibrate at its own natural frequency as a result of vibrations it has received from other sources of the same frequency. Now, take note of the fact from this case of resonance that every particular system has its natural frequency. Now, when it experiences what we call superimposition means when it is under the influence of vibrations from other sources, it causes it to vibrate as well. We have the second kind of forced vibration, which is resonance in strings. You see, stationary waves can occur on a stretched string or wire, and this we can obtain by varying the driving frequency of the string. That's what we call resonance in strings. Let's look at musical instruments now and how they are able to produce sounds. We have different kinds of musical instruments. Let's start with wind instruments. As the name implies, it simply means sound from wind. Put simply, wind instruments are instruments that generate sounds from wind. We have examples such as clarinets, flutes, saxophone, trumpets. They are all examples of wind instruments. They all originate from air vibrating over an opening in the instance of an organ and a flute. They also originate from the vibrating lips of a brass instrument, for instance, say a trumpet. They also originate from a vibrating heel in the case of a clarinet or saxophone. They are also made up of what we call air columns. Now, some of these air columns have fixed lengths, some have their lengths varied. Their resonance frequencies can be altered by opening or closing of holes in that column, and that's why when you see people playing trumpets or saxophones, they tend to put their fingers on some buttons on this area. They are either trying to vary or restrict the airflow, which in turn causes different kinds of sounds to be produced. We have stringed instruments. Stringed instruments are instruments that are designed to produce sound when they are set in vibration by a bow or when they are plucked by a finger. You can see from the diagram here we have the guitar itself. We also have the violin. Violin is bowed while a guitar is plucked. Now, the frequency of a vibrating string depends on its length, its mass, and the force that keeps the string in place. So these vibrations produce both what we call the fundamental frequencies and the overtone frequencies. And of course, we also have the percussion instruments. Percussion instruments are instruments that produce musical notes when they are struck or hit. They have what we call rods, they have plates, they have membranes that vibrate when they are struck. Examples are drums, bells, or the one we call talking drums. Examples are xylophones and some drums that have membranes in them. Let's talk about echo. I'm sure you must have heard about echo before now. And echo is a situation where if you've ever been into an empty hall and then you raise your mouth, your voice, and then you start talking, it's as if some people are repeating what you've said, or you hear other sounds of your voice repetitively. So an echo, put simply, is the repetition of sounds caused by the reflection of sound waves from a hard surface such as buildings, walls and cliffs, which are very good reflectors of sounds. Echoes have a practical importance in the development of what we call sonar, speed traps, prospecting for oil, and determining the speed of sound. In fact, in oil exploration, echo is used by geophysicists to know where oil is particularly located inside the ocean. So in the determination of the speed of sound by echo, we use the expression here 2x equal to vt, where v is the velocity of the sound, x is the distance between the source of sound and the reflecting surface, and t is the total time that has been taken for this echo. And then we have vibration in strings. Remember, sound wave is generated from a fixed string that is allowed to move at the other end, while one end is used to control the frequency of that sound. We've also learned that we have what we call the fundamental frequency, which is the natural frequency that an instrument will always have, or a closed system will always have. Now, the distance between two successive notes in a string is known as wavelength divided by 2. This is a Greek alphabet called lambda, wavelength divided by 2, and it is equal to the length of the string, which is L. So you can say wavelength divided by 2 or wavelength equal to 2L at any point in time. Now let's talk about vibrations in a closed pipe. In a closed pipe, only odd numbers of harmonics are present as overtones accompanying the fundamental note. The possible harmonics are, we have the F with subscripted O, 3F, 5F, 7F, where this F here is called fundamental frequency. So 3 times the fundamental frequency, 5 times fundamental frequency, and so on and so forth. Fundamental frequency, on the other hand, can be given as F equal to the velocity over 4 times the length. Also, in an open pipe, the harmonics present are this 2, 3, 4, 5 respectively, which means that both odd and even harmonics are present as overtones. To get more information, please visit the notes attached at the end of this video. Thank you very much for joining us in this lesson. To refresh your memory on what we've just discussed, please take the tests that will appear on your screen.